Hello student, previously we had learned about canonical correlation analysis. So now we will see the multidimensional scaling by classical approach. This video will explain to you what is the classical multidimensional analysis and the example of it. Enjoy the video!
Today we will learn about the multidimensional scaling. We go through about the classical MDS, that is multidimensional scaling. So next. First, we want to about the classical multidimensional scaling. This can be considered to be an alternative to the factor analysis. So the difference between the multidimensional scaling and the factor analysis is the MDS is the concept of distance, that is similarity and dissimilarity between the investigated object, and the factor analysis is the similarities between the object that we express in the correlation metric. In classical MDS, the data are not distant as measured from a map, but are rather proximity, that's similarity and dissimilarity data or metric. So the objective of the MDS is to determine the dimension of a model, so that the model will give a good fit for the observed proximity. So if the dimension we get 2, 3 or more. So then algorithm for the classical MDS, we have this formula, that is B equal to the X, the raw data, times is the X transpose. And then for the element of Bij is the element of the B. So the element you calculate from this formula, that is summation of Ik times with the Ijk from the K equal to 1 to the Q. So this is the square distance that we want to calculate, that is VII plus BJJ minus 2BIJ. Then after we go through about the raw data and then we do analysis, we get a new B, that is the V1 times the lambda 1 and the V1 transpose, where the V1 is the content of the first Q eigenvector, and then the lambda 1 is the non-zero eigenvalue. So this is the coordinates, and then X is equal to the V1 times the square root of lambda 1, where the lambda 1 is the value of square root of eigenvalue. So after that, we want to find the m-dimensional that represent by the size of the proportion. So if the value of the proportion is 0.8, so it suggests a reasonable fit.
Now, as you had understood the concept of classical multidimensional scaling, we will proceed with the example so that you can see the application of classical MDS.
Then I will continue about the topic, the classical multidimensional scaling. So I will explain to all of you the way how to make multidimensional scaling using R. So X is a metric of, so we insert the metric into R by using this command. So you can see the number of row 10, number of column 5 by row through. You learn all of this in computing classes. Next. So we got the distance matrix by the function distance x. So we get the distance of the matrix. By using the CMD scale function, we set k equal to 2. Therefore, we get 2 points, and we get the eigen values positive up to 7. Next, we plot the data, and we believe that 7, 6, and 10 have relationship. We use the CMD scale function, and this time we set k equal to 9. we get the eigen value positive up to 7. So we get this output.
Why we have to do the proportion?
We do the proportion to find the optimal number of dimension. Previously, we get the eigenvalue positive up to 7. So we need only 3 value to get the optimal number of dimension. So the optimal number of dimension is 3.
So, you had see what is classical multidimensional analysis and its example. Now, we had arrived at the end of this video. We hope that you will understand this topic clearly. If you have any questions, please leave the comment below. Like and share our video. Until we meet again.